we talked about formulas and compounds and how to name compounds. And we've talked about electrons and how they have an effect. We haven't quite talked about how they have an effect on bonding, but we've talked about how electrons, their electron configuration is different depending on what the atom is. And that configuration will lead to specific bonding. If we use these upcoming bonding theories that we're going to talk about, we can actually start to predict what some of these shapes are. Now, these shapes that you can see over here on the right are much more complicated than anything we're going to see. That's more organic stuff. But it's the same principles that apply to these more complicated molecules also apply to the stuff that we're working with. So bonding theories are a series of theories that help us to predict how atoms bond together in order to form compounds. Because in general, atoms, they kind of come together in a consistent way, in a somewhat predictable way. Yes, there's always that one offshoot of, oh, it doesn't satisfy an octet or it's acting kind of strange. But in general, things tend to kind of combine together in a consistent way. Bonding theory helps us to predict why salt is NaCl. And not NaCl2. We kind of already know that from like the flip-flopping with the charge neutrality. You can also prove it with these bonding theories, but I think that the bonding theories are in general just more useful for non-metal stuff, like H2O, H3O, anything where you have two non-metals combined. So why is water H2O and not H3O? What are the properties of H2O? So bonding theories will also help us to explain some of the shapes of these molecules, and the specific shape of the molecule will have deterministic physical and chemical properties. So if it's shaped in one way versus another way, it will behave differently. So the first theory we're going to start with is the Lewis theory, or the Lewis dot theory. And this was invented by a guy named Lewis, and he represented electrons as dots that were drawn around a symbol. So we would write the symbol, like, let's say for phosphorus, and we would put dots around it to represent how many electrons were available to bond. Super simple model, but had really, really tremendous predictability power. So we were able to predict a lot of shapes using these. It can determine whether a partial set of atoms will form a stable molecule. It'll also help us to determine what the molecule will look like. There are more advanced theories always, but this will do it for us. So we want to first be able to do a Lewis dot structure. In a Lewis dot structure, we're going to put the total number of valence electrons around the symbol. Now remember, valence electrons are not all of the electrons. It's just the electrons that are in the outermost shell. So if we look at oxygen, this is the electron configuration for oxygen, 1s2, 2s2, 2p4. Now, to figure out what the valence electrons are, we look at the highest orbital number and we add up those electrons. So 2 here and 4 here gives us a total of 6 valence electrons. So if I was to draw the Lewis structure, I would write the symbol for oxygen, and then I would have 6 dots around it. Now, you want to think of the Lewis dot structures as existing in 4 quadrants. So top, bottom, right, and left. You always fill an electron in singularly, and then we go back and double up. Okay, so we wouldn't have 2 electrons here, 2 electrons here, and then 2 electrons here, because then this side is like imbalanced. And again, the electrons want to get as far away from each other as they can. So we first fill up singularly, then we go back and double up. Now, writing these electron configurations to figure out the number of valence electrons is a total pain in the butt, especially when we get into some of those heavier, bigger molecules. So instead of writing the electron configuration, just know that you can go with whatever the main column group is, and that's the number of valence electrons. I don't know if I have a slide here with the periodic chart. I sort of have one here. Yeah. So if you're in column 1, you have 1 valence electron. You're in column 2, 2 valence electrons. Column 3, and I'm referring to main group, so we skip over transition metals. Column 3 will have 3 valence electrons. 4 will have 4 valence electrons, so on, all the way to column 8. Column 8 has 8 valence electrons, minus helium. Helium has 2 valence electrons, but he's happy with 2 valence electrons, okay? So outside of helium, neon, argon, krypton, xenon, all of those have 8 valence electrons. And remember, everything is trying to bond or connect in a certain way so that it can also have 8 valence electrons. All these guys, they don't have 8 valence electrons, but they want 8 valence electrons. So we're going to try and bond things together to satiate these octets. So oxygen being in column 6, you can just jump to the conclusion that it has 6 valence electrons. That's what I would do. I would not write the electron configuration out. I would just go with whatever column you're in. So let's look at some of the other ones we have here. This is just talking about what I had already said about filling the dots in singularly first. So fill 1 electron in each of those 4 quadrants and then go back and double up. It's important to do that in the homework too, or mastering chemistry will get mad. All right, so these are the first few atoms. We've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Lithium is in column 1, so we give it 1 valence electron, 1 dot. Beryllium is in column 2, so we give it 2 valence electrons. Boron, column 3, 3 valence electrons, so on, all the way to neon. If you look at neon over here, it's in column 8. It has 8 valence electrons, so 2 in each quadrant on each side. That is very, very stable. All right, that is that configuration where you have 8 valence electrons like that forms this thing over here called an octet. Oct for being 8. All right, so everything else is going to try and attach itself to something so that it can become like an octet. So if we were to write the Lewis dot structure for phosphorus, phosphorus is in the same column as nitrogen. Okay, it's not the same as nitrogen, but it's in the same column as nitrogen. It's in column 5, so it will also have 5 valence electrons. You can see nitrogen here has 5 valence electrons, and then phosphorus will also have 5 valence electrons. Helium is an exception to what we call the octet rule. Helium is happy with just 2 electrons, okay? And the electrons will be paired together because it's the 1s, and there is no p orbital on floor number 1 or the first floor. It's too close to the nucleus. The only thing we can get is that tiny sphere. So helium is okay with 2. This is known as a duet. There's a couple other atoms that are okay with just 2 electrons. They're really small. Hydrogen, helium, lithium, sometimes beryllium. Those first couple of atoms, they're okay if you satisfy them with a duet. They don't want an octet. They're too small for an octet. But everything else is going to want an octet. So you're going to mix and match and combine things to get octets, unless it's one of the first 3. So in Lewis theory, we can kind of get a better idea of chemical bonding. And a chemical bond is when there's some sort of sharing or transferring of electrons. If we have an ionic bond is where we transfer 1 electron to the other. So this is a metal combined with a non-metal. So I don't use Lewis theory a whole lot for ionic bonding. It seems like a little excessive, especially when we've got that flip-flopping method, which is so much faster, but I'll briefly go through it in ionic. But I think that the Lewis theory is really, really valuable for covalent bonding. So molecular stuff, when you have 2 nonmetals, anytime you're sharing electrons, this is like, it's really, really useful for that. So in Lewis theory, everything is going to combine, move around, share, exchange electrons in order to fulfill or observe the octet rule. And the octet rule is that atoms will share or transfer electrons in order to obtain 8 outer electrons. The octet rule generally applies to all the main group elements, except for hydrogen, lithium, and beryllium. Okay, those guys, again, the small ones, they're okay with a duet. They're okay with just 2. So when a metal bonds with a nonmetal, electrons get transferred from the metal to the nonmetal. The metal becomes a cation, it becomes positively charged. The nonmetal becomes an anion, which is negatively charged, and then they stick together, right? They attract each other. So we can see this happening with Lewis structures. Again, I think this is a little bit overkill, doing it with a Lewis structure, but let's check it out. So here's potassium, and potassium is in column 1, so it has 1 valence electron. Chlorine is in column 7, so it has 7 valence electrons. So what happens is this single electron from the potassium gets moved over to the chlorine. What happens now is the potassium is down 1 electron. So we're going to give it a charge of plus. It has a complete octet. It isn't written in, but it has a complete octet from the onion layer below, right? From the octet below, the closer one to the nucleus. So if we strip off this sort of unfulfilled electron here, underneath it is a complete shell. So potassium, by getting rid of an electron, has now formed an octet. That electron moves over to the chlorine. Well, now chlorine, instead of having 7 valence electrons, it now has 8 valence electrons. And those 8 valence electrons make an octet. So this has an octet and this has an octet. This has a positive, this has a negative, and then they stick together. A lot of work when we kind of just know potassium is in the first column, chlorine is in the last flip-flop KCl. That's sort of how we've been doing things thus far. Let's look at another one of these. Magnesium and oxygen. So magnesium is in column 2. It has 2 valence electrons. Oxygen is in column 6, so it has 6 valence electrons. When these two things come together, these 2 electrons are going to get transferred over to the oxygen. Magnesium will be down 2 electrons, making it a 2+ charge, and it has a complete octet from the previous shell. Oxygen has gained 2 electrons, so it's filled those open empty spots, and now it also has an octet. So both of these are satisfying their octet. This has a 2+ charge, this has a 2- charge. They come together and form MgO. Again, really a lot of work to just be able to go Mg is a 2+, O is a 2-, flip-flop, we get Mg2O2, which reduces down to MgO. Last one, sodium combined with sulfur. So sodium is in column 1. It has 1 valence electron to give. Sulfur is in column 6. So it has 6 valence electrons. So sodium, it's not going to eat 7 electrons. It's just going to give up its 1 electron. Sulfur isn't going to give up the 6 electrons. It's going to try and eat 2 electrons to get an octet. So what happens is this sodium will move over, or I'm sorry, this electron will move over here. Then that will make the sodium happy. The sulfur, though, isn't completely satisfied. He has now 1, 2, 3, 4, 5, 6, 7 electrons. 7 electrons, so close. So what ends up happening is another sodium will come around and give an electron. So we actually end up having 2 sodiums transferring the electrons over for every 1 sulfur. That allows each sodium to have an octet from the previous set, and the sulfur has its octet by now filling its current shell. Again, doesn't that seem kind of like a lot of work when we can go Na has a plus charge, sulfur has a 2- charge, flip-flop, we get Na2S. They have similar predictability power, and I just feel like this is a lot faster. So I'm not going to spend a whole lot of time on the ionic stuff. You'll probably see it in the homework, but you're not going to see it on your lab from this week, and I don't test you guys on it, so don't worry about it for the exam. All right, this is where we like to use the Lewis dot structure, though, when we have a covalent bond or 2 nonmetals. So when nonmetals bond with other nonmetals, they form a molecule, and these molecular compounds contain covalent bonds where the electrons sit in the middle and they're shared. So instead of, like when we have a metal and a nonmetal, the metal says, I don't even want the electron, just take it. And the other guy's like, sure. In this case, well, they're both nonmetals. They both have negative charges. They both want to have access to those electrons. So they have to instead put them in the middle and share them. In Lewis theory, we're going to create covalent bonds by allowing neighboring atoms to share some of their valence electrons in order to obtain an octet, 8, or if you're hydrogen, a duet. So let's look here at hydrogen and oxygen. So currently, when we draw our Lewis dot structures, we've got hydrogen, and it has 1 valence electron because it's in column 1. Oxygen has 6 valence electrons because it's in column 6, right? So 6 electrons here and 1 electron here. Now, the hydrogen isn't going to transfer the electron over. Why? Because the hydrogen wants 2 electrons, like it wants to have access to electrons as well. So instead, the hydrogen says, well, I'm not going to give you my electron, but why don't we share these two? Okay, why don't I move a little closer and we'll make a bond where we share these 2 electrons. Now hydrogen gets access to 2 electrons, and then the oxygen also is getting access to 2 of those electrons. So hydrogen is good. He's fulfilled his duet. Oxygen, 1, 2, 3, 4, 5, 6, 7, almost there. So what happens is another hydrogen comes in and says, hey, no, you know what? I'll share my single electron too, and then we can all be happy, right? So if we look at this situation here, the oxygen has access to 8 electrons, and the hydrogen also has access to, well, not 8, but each hydrogen has access to 2 electrons. So these 2 are fulfilling their duet, and the oxygen is fulfilling its octet. So they're all getting what they want by sharing the electrons. Sometimes instead of writing the dots like this, we'll write the bonded electrons as a line. So there we are sharing them. The bonding pairs, the electrons that are being shared between 2 adjacent atoms, will get a line. Just know that this line here represents 2 electrons, not 1 electron, okay? So each of those is 2 electrons. If that feels sort of like, how did you do that? You just sort of moved them together and did some magic. I will show you that there is an actual system to follow so that you do it correctly every time. But for right now, let's just look at the difference between bonding pair and lone pairs. So on this central atom here on oxygen, any electrons that are included in the bonding system are known as bonding pair electrons. Any electrons that are on the central atom, but they don't have a partner, like there's no hydrogen attached to these, we call these lone pairs of electrons. And those are important. They have an effect on the shape, which we'll talk about a little bit later. So we want to be able to identify bonding pairs and lone pairs. If I do ammonia looks like this: nitrogen and 3 hydrogens. They're bonded together, and then there are 2 things here. I would say that there are 3 bonding pairs and 1 lone pair. Okay, you want to be able to identify those, bonding versus lone. All right, let's talk about the diatomics. I'm going to move over my whiteboard. So we're going to look at the diatomics: chlorine, oxygen, and nitrogen. So all of these form diatomics. Why do they form diatomics? Well, chlorine is in column 7, so it has 7 valence electrons. It's so close to being stable. It's not, though. So what happens is another chlorine comes around who also has 7 valence electrons and is like, well, why don't we share these 2 electrons? Let's bond, let's stick together. And so what ends up happening is this chlorine has access to 8 electrons, 2, 4, 6, and 8. And this chlorine has access to 8 electrons, 2, 4, 6, and 8. So by them sharing, they were able to, they didn't have to make electrons up out of thin air. They were just able to share 2 of their electrons to each get an octet. Oxygen is in column 6. So each oxygen has 6 valence electrons. So I've got another oxygen over here that has 6 valence electrons. So this oxygen says, hey, why don't we share some electrons? Okay, so they share this as a bond. Now, this oxygen over here has access to 2, 4, 6, 7 electrons. And this one also has access to 7 electrons. So they're closer to the octet, but not quite at the octet. So what these oxygens are going to do, they're going to take these electrons and they're going to move them over here and make what's known as a double bond. Okay, so I'm going to erase this set of electrons here and here, and I'm going to put it in between them so that they can share. Now we've got an oxygen double bonded to another oxygen. Double bonds are stronger than single bonds, okay? Single. Double bonds contain 4 electrons. Single bonds just contain 2 electrons. Again, I will show you in a little bit how to know when to make a double and a triple bond. For now, sort of just trust me with this. Nitrogen is in column 5, so he has 5 valence electrons. So we've got nitrogen, 1, 2, 3, 4, 5. All right, I have another nitrogen over here. 1, 2, 3, 4, and 5. So these 2 nitrogens are going to be more stable if they connect. They're going to take a pair of electrons and they're going to share them. This nitrogen over here has access to 2, 3, 4, 5, 6. Okay, getting closer, but not at an octet. So they're going to share another set of electrons. I'm going to erase these guys and I'm going to stick them in the middle. Now this nitrogen has access to 1, 2, 3, 4, 5, 6, 7 electrons. All right, we're almost there. What are we going to do? We're going to share another pair. And again, I will show you how and when to do double and triple bonds. So now we're going to throw this here. This is known as a triple bond. It contains 6 electrons, stronger than a double bond. It's shorter than a double bond. You can't have a tetra bond. Okay, there's nothing more concentrated than a triple bond. So single bonds are usually what you're going to see, but sometimes we get double bonds and sometimes we get triple bonds. And again, I will show you when to apply double and triple bonds. But this is why we find these things as diatomics, because when they stick to themselves, right, or they stick to a buddy, they find a stable configuration. So there's our chlorine with our single bond, satisfied. Oh yeah, hydrogen also does this too, right? Hydrogen is a diatomic. Hydrogen has a single electron because it's in column 1 valence electron. So if 2 hydrogens get together, they each bring their single electron and now they share. They both have access to 2 electrons. Again, remember, hydrogen is happy with a duet. Then we talk about oxygen with its double bond. And we talk about nitrogen with its triple bond. Double bonds in general are shorter and stronger. Triple bonds are even shorter and even more strong. You don't need to know like the picometer distance or anything like that. Okay, so what we did here was we made Lewis dot structures for really simple molecules. We're going to make some Lewis dot structures for some more complicated molecules. And there is a way to do it so that you do it correctly every time. All right, we're going to do the Lewis dot structure for water. So write the formula for water somewhere. I'm going to write it up here, H2O. When we are trying to make a Lewis structure for this, the first thing we want to do is write the correct, what's called skeletal structure. So this is just sort of like loosely putting the atoms in relative order. In nature, oxygen likes to be a central atom and hydrogen likes to be what's called a terminal atom, meaning that hydrogen likes to be on the outside. Why does hydrogen like to be on the outside? Because hydrogen only wants to have 2 electrons. If we stick hydrogen in the center of the molecule, it's going to force it to have too many electrons. So we always create hydrogen on the edges and usually oxygen's in the center. It's not always though, but definitely hydrogen is a terminal. So my skeletal structure is going to look something like this. Oxygen in the center and then hydrogens on the side. You could draw it like this, oxygen in the center and hydrogen above and below. These are 3-dimensional molecules that you can rotate in space. Okay, so if I see this and I see this, I am seeing the same thing. So the only way to know the absolute correct skeletal structure is to examine the structure in nature using like a microscope or something, an electron microscope. But we're good just with this idea of, hydrogen liking to be on the outside. There's another rule too. In general, things in nature like to be symmetrical and balanced. So we'd like to put the single, whatever we have single in the center, and then multiples usually go on the outside. So if I have let's say we have SO3. I'm probably going to put the sulfur in the center and the oxygens on the outside. That makes it much more balanced looking than, say, an oxygen in the center, a sulfur on one side, and 2 oxygens on the other side, right? That's not very balanced. This is much more balanced and neat. So go with something that looks symmetrical. All right, so write the correct structural formula. Some more said hydrogen is a terminal atom. Most molecules have a symmetrical quality to them. Are there exceptions to these rules? Always, 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 always. But it covers 90% of the molecules out there, 95% of the molecules out there. So after you've drawn your skeletal structure, so we have H2O, and we said we're going to put hydrogens on the side and oxygen in the center. You need to figure out how many electrons you get to kind of mess around with or play around with. The number of electrons that you get to play around with for this given molecule is calculated by totaling up all the valence electrons brought to the molecule by each element. So hydrogen is in column 1. So hydrogen will bring 1 electron. How many hydrogens are there in this molecule? There are 2 hydrogens in the molecule. So I do need to multiply that value by 2. Okay, you multiply it by whatever the subscript is. Then I'm going to add that to the number of oxygen valence electrons. So oxygen is in column 6. So oxygen will bring 6 electrons. All right, 1 times 2 is 2 plus 6 gives me a total of 8 valence electrons. Any questions on that? We'll do some more of them, but any questions on where I got this 1 from, or this 6 from, or this 2 from? Okay, the 1 is related to the hydrogens column. The 2 is because we have 2 of them. The 6 is oxygens. What did I want to say? I wanted to say something and I can't remember. Transition metals and stuff, it's not really going to affect you. So don't worry about that. Okay. So I have 8 valence electrons. That means that when I finish my structure, it has to have 8 valence electrons, or it has to have 8 electrons arranged in some sort of order. I can't have 10 electrons. I can't have 6 electrons. And the other thing I wanted to note. So oxygen brings 6 electrons, but how many electrons does he want? He wants 8. Okay. Hydrogen brings 1 electron, but he wants 2 electrons. It's kind of like, you're bringing a dish to a potluck party, but you want to eat like a bunch of stuff. You want to get more out of it than you've brought. Okay. So these guys bring the number of valence electrons they have, but they all want either 8 or 2. So just don't confuse, because sometimes people will see, well, oxygen has 6, so he only is going to want 6 electrons, right? No, he brings 6 to the party. He wants to take 8 back with him. That's why he's going to the party. That's why he's making a molecule. So if you are writing a Lewis structure for a polyatomic ion, you must take into account the charge of the polyatomic ion. We'll come back to this in a minute. Okay, we'll come back to that. So once you have a skeletal structure and you have the total number of valence electrons, we now need to figure out where we put the electrons. And there's a specific system. The first thing you want to do always is stick the thing together. Because if it's a molecule, right, if we're writing the formula, it has to be stuck together. So draw a bond connecting the things together. I know at least 4 electrons have to be dedicated to bonding it together because it's a molecule. The next thing is that you always want to make the outer guys happy first. So check and make sure the outer guys are happy first. If they're happy, then you go and make the inner guy happy. Don't work from the inside out. It just doesn't play out well. Okay. We always want to make sure the outer guy has enough electrons. Then we check and see if the inner guy has enough electrons. So hydrogen. Is hydrogen happy with this bond? It is. This bond has 2 electrons in it. And how many does hydrogen want? Hydrogen just wants a duet. Okay. So this hydrogen is happy the way it is. This hydrogen here is also happy the way it is. It has access to 2 electrons. Okay, so I'm not going to add any electrons to the hydrogen. Oxygen, is oxygen happy the way it is right now? It's not. It only has 4 electrons, right? 1, 2, 3, 4. How many does oxygen want? It wants 8. And I have to have 8 electrons on the board, so I need to put these electrons somewhere. So I'm not going to put them on the hydrogen. I'm going to put the remaining 4 electrons on the oxygen. So I'm going to put 2 here and 2 here. If you did it like this, if you put 2 electrons on the top, and 2 electrons on the bottom like this, that's okay. That's also saying the same thing. It's the molecules rotated in space. What you cannot do is this. You can't put like 2 on the top, 3 on the top and 1 on the bottom. They're always paired together. Okay, so pair them together. So when you think you're done with your molecule, check and make sure you have the correct number of electrons on the board. So I need to have 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. 8 electrons are on the board. Then double check and make sure everybody's happy. Hydrogens have access to 2 electrons, so they're both happy. Oxygen has access to 2, 4, 6, and 8. So now oxygen is happy. So we were able to make the water molecule. Any questions on that, on what I did there? We will do some other ones, but just any questions on why I put things where I put them? Okay. If you do, you can throw it in the chat. We will do a Lewis dot structure in a minute. If any atom lacks an octet, form a double or a triple bond as necessary. I will show you guys this in a minute. So let's do, we'll do CO2. Okay, CO2. I tend to calculate my valence electrons before I make the skeletal structure. It doesn't really matter. You can do the skeletal structure or calculate them. Carbon is in column 4. So it brings 4 valence electrons. Okay. I'm going to add that to the oxygen. Oxygen is in column 6. It brings 6 valence electrons, and there are 2 of them. So I do need to multiply by 2. So we get a total of 16 electrons. Are you all good with how I got to 16 electrons? Seeing yeses. Okay, good. So that's not up for negotiation. You have to have 16 electrons / dot lines in some combination. I can't make it 18. I can't make it 14. Now I'm going to draw a skeletal structure. So to create a balanced structure, I would put carbon in the middle and I'd put oxygens on the side. Oxygen, in some instances, is in the center. In some instances, it's not, okay? Really, we want to just create something that's symmetrical. After I've drawn my skeletal structure, okay, first electrons you put on the board are the bonded electrons. So go ahead and stick the thing together because it's a molecule. So it's got to be stuck together in some way. Then we want to make the outer guys happy first before we work to the center. So this oxygen right now, is he happy? No. He has access to 2 electrons. How many does he want? 8. So I'm going to add 6 electrons to this oxygen. 1, 2, 3, 4, 5, and 6. Plus the 2 in the bond gives me 8 octet. Okay, this oxygen is good. Now I'm going to move over to this oxygen because again, I'm going to make the outer guys happy and work inward. This oxygen only has 2 electrons right now. He wants, no brainer, 8. Okay, so I'm going to add 6 more electrons. 1, 2, 3, 4, 5, and 6. This oxygen is happy, and this oxygen is happy. How many electrons do I currently have on the board? 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons on the board. I cannot add any more electrons. Okay. Oxygen's happy. What's going on with carbon? Is carbon currently happy? Is he meeting his octet? No, carbon right now only has access to 4 electrons. Can I add more electrons to the board like this? No, I have to have 16. This is a structure that has 20. That's no good, okay? So we don't want to do that. What needs to happen here is that these oxygens on the sides need to be a little more generous, all right? This oxygen has to say, you know what? I'm going to share a bond. Okay, I'm gonna share these electrons and we can make a double bond. You never make double bonds, you never make triple bonds until you've put every electron on the board. First, get all the electrons on the board and then ask yourself if you need to double or triple. So I'm gonna take those 2 electrons that were on the side and I'm just gonna scoot them over here. I haven't changed the number of electrons on the board. There's still 16 electrons on the board. I've just moved these over so that now carbon has a little more access to them. Okay, the oxygens are still good. The carbon is closer to being happy, 2, 4, and 6, but he wants 8. So this oxygen over here is going to go ahead and share a set of electrons. I'm going to erase one of these and then redraw it. These problems are usually better done in pencil because you do have to like erase stuff and move things around. Anytime you make double bonds or triple bonds, always check and make sure that you haven't like accidentally added or gotten rid of electrons. So do I still have 16 on the board? 2, 4, 6, 8, 10, 12, 14, 16. I still have 16 electrons on the board. I just sort of rearranged them. Are the oxygens happy? They're still happy. 2, 4, 6, and 8. It didn't give the electrons away. It's just sharing them with the double bond. So this thing has access to 8 electrons. This thing has access to 8 electrons. And carbon in the middle has access now to 2, 4, 6, and 8. All of them are happy. Huh? Question? No, just do some practice with them. Let's do, I think in the slides, the next thing it talks about, is it cyanide? Hello. Hello. We did our CO2. Yeah, let's do cyanide. So cyanide is a polyatomic ion, CN with a minus charge. And it's C capital N. Some of you guys on the homework or on the lab made it C lowercase n. Make sure that's a capital N because it's carbon and nitrogen. And this whole thing has a minus charge. So in the slides, it said, hey, if it's a polyatomic ion, you have to do this extra thing. What is that extra thing? Well, we're going to take the valence electrons of carbon, which is 4. We're going to add it to the valence electrons of nitrogen. Nitrogen is in column 5, so 5 valence electrons. If it has a negative charge, that means we have to add 1 electron. We add an electron for every negative charge. We subtract an electron for every positive charge. If I didn't include this, I would end up having 9 electrons, and that would be weird, right? Because everything is in pairs. So we really want to have even numbers here. So 4 coming from the carbon, 5 coming from the nitrogen, and then an additional electron coming because it's a -1 charge. So my total electron here is 10 electrons. When I draw this structure, I'm going to put cyanide, or sorry, I'm going to put carbon and nitrogen. It doesn't matter if you did it like this, nitrogen and carbon, that's okay. If you did it like this, carbon and nitrogen, again, totally fine because we're in 3-dimensional space. I'm just going to stick with that first one. So what do I do? Right off the bat, stick it together. Right? We make our bond. Then we quote unquote make the outer guys happy. There's no like particular outer one here because there's just 2 of them. So just pick one of them. So I'm going to pick the nitrogen. Nitrogen right now has access to 1, 2 electrons. I'm going to give him some more electrons, specifically 6 electrons. 1, 2, 3, 4, 5, 6, and then the 7 and the 8 in the bond give him the octet. I have 2 more electrons that I need to put somewhere because I need to use 10 electrons and there's only 8 on the board. So I'm going to put the last 2 here at carbon. There are now 10 electrons on the board. I cannot add any more electrons. I don't want to subtract electrons. Nitrogen is happy. Is carbon happy? Carbon right now has access to 4 electrons. Yes, he brought 4 electrons to the party, but he wants 8 electrons. So we need to figure out a way to get carbon more electrons. I can't draw more electrons on the board because I can only have 10 electrons. So what do we do when we're short electrons? We make double or triple bonds. Nitrogen's it just has to be generous. So let's take one of these pairs over here and let's move it into the center so that it can share it with carbon. Nitrogen still has access to its 8 electrons. Carbon has access to 6 electrons. So it's getting closer, but not quite there. Okay, so nitrogen needs to be even more generous. It needs to take another pair and stick them in between. Again, anytime I move electrons around, I just always double check and make sure that I haven't done something to the total number. So I need to have 10 electrons, 2, 4, 6, 8, 10. We still have 10 electrons on the board. Carbon has access to 2, 4, 6, and 8. Carbon is happy. Nitrogen has access to 2, 4, 6, and 8. Nitrogen is also happy. So this is the structure. Because it's a polyatomic ion, the last little detail is to put it in brackets, the whole thing, and then just put the charge around the outside of it. So put the -1. Because if you don't do that, technically the reader is going to look at it and say, hey, this is carbon and nitrogen. Why do you have 10 electrons? You should only have 9 electrons. When you put it in the brackets with the charge around it, you're letting the reader know, oh, no, it's not just carbon and nitrogen. It's actually cyanide, the polyatomic ion. So in that case, we had to make a triple bond. Again, rule of thumb, do not put a double or a triple bond on until you need it. If you don't need it, don't use it. If you have enough electrons, use the electrons. Okay, so I'm going to give you a couple molecules and I want you to do the Lewis dot structures for them. pH3, NH4 plus, and what do I want to do? CCl4. Okay, so I'll give you guys like 7 minutes for this. Calculate the total valence electrons you get to play around with. Make a skeletal structure, stick it together, make the outer guys happy, make the inner guy happy. Give it your best. All right, so hopefully you're able to do something. Maybe it wasn't correct, but we will make sure it gets correct. So pH3. All right, I calculate my valence electrons first. Phosphorus is in column 5, so it brings 5 valence electrons. Hydrogen is in column 1, so it brings 1 valence electron, and there are 3 of them. So I multiply by 3, which gives me 8 electrons. I like that. All right, to keep it balanced, I'm going to put phosphorus in the center and the hydrogens around it. Also, that's symmetrical, and hydrogen doesn't want to be in the center. You put hydrogen in the center, you're going to make him have too many electrons. Okay. Next thing to do, stick it together. So bond, bond, bond. Make sure the outer guys are happy. Hydrogen is happy with just a bond because he has 2 electrons. And remember, hydrogen likes a duet. I have 6 electrons on the board. I need 8 electrons. Where am I going to put those last 2 electrons? I'm going to put them on phosphorus. And phosphorus wanted 8 electrons anyway, so we killed 2 birds with 1 stone. So there are 8 electrons on the board, and everybody is happy. NH4 plus, this is a polyatomic ion. Nitrogen brings 5 electrons. Hydrogen brings 1 electron, and there are 4 of them. There's a plus. The plus really means minus. We want to subtract 1 electron, right? So this has 8 electrons. If you did 10 electrons, it's going to get you into trouble. You're going to have a hard time figuring out where they go. So we have 8 electrons. I'm going to put the nitrogen in the center and the hydrogens around it because that looks balanced and hydrogen doesn't want to be in the middle. Stick it together. And by sticking it together, I've actually used all my electrons. Are the hydrogens happy? They are. Is the nitrogen happy? Yes, 2, 4, 6, and 8. It's happy. So I'm going to just put it in brackets. I'm going to give it a plus. And that thing is done. Over here, this has a very similar shape to this one. Carbon brings 4. Chlorine is in column 7, so it brings 7, and there's 4 of them. So 28 plus another 4 is 32 electrons on the board. Yowza. Okay, so we have to have a home for 32 electrons. I'm going to put carbon in the center, and I'm going to put the chlorines on the side. That will make it look neat and balanced. First thing we do, stick it together. Bond, 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 bond. Then I'm going to make the outer guys happy. So let's go pick a chlorine. Chlorine wants 8 electrons. Right now, he only has 2. So we need to give him 6 more. 1, 2, 3, 4, 5, 6. This chlorine also wants 8 and only has 2. So we'll give him 6. Same thing with this chlorine. We just sort of repeat the pattern around, and then the final chlorine also wants access to a total of 8. How many electrons do I currently have on the board? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. 32 electrons are on the board. Is everybody happy? Well, I know the chlorines are happy. I mean, I gave them the correct number of electrons to make them happy. So I really kind of just need to check the middle guy, carbon. And is carbon happy? He is. 2, 4, 6, 8. We're done. If you're wondering, is she really gonna like count all those like little dots on her labs? Yes, I will. So put them in the right spot. Questions on these? No. Okay. We're gonna do one more together to show us something called a resonance structure. Okay, so SO2. This one's going to do something a little funky. Let's count up the valence electrons. So sulfur is in column 6, so it brings 6 valence electrons. Oxygen is also in column 6, so we bring 6 valence electrons, and there are 2 of them. So in this structure, we have a total of 18 electrons. I am going to make my skeletal structure. So sulfur is going to go in the center and oxygen is going to go on the sides. Anyone have questions on that? You feel like that's kind of what you would do? We've got a balanced skeletal structure and we counted up our valence electrons. Okay. We're going to follow the same system of sticking it together and then making the outer guys happy. So we'll stick this and this together. Gosh, those are really like far apart. Let me consolidate this thing just a little bit. Oxygen bonded to sulfur and a sulfur. No, not anywhere remotely close to what we're doing. Sulfur bonded to an oxygen and an oxygen. Okay, so let's make the outer guys happy. So pick an oxygen. I'll pick this one over here. He has, right now he only has 2. He wants 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to give this oxygen an additional 6 electrons as well, so that he has access to 8. I currently have 16 electrons on the board. How many electrons need to be on the board? 18. So I have 2 more electrons that I have to put somewhere. I can't put them on either of those oxygens. Those already have their octet. So I'm going to put the last 2 electrons right on sulfur there. I have 18 electrons on the board. Done. Well, almost. We're done with the electrons. Now we have to see if everybody's happy. This oxygen is happy. This oxygen is happy. Sulfur is not happy. Sulfur is close to being happy, but it needs another pair of electrons. So the oxygens need to share. If we classify this as oxygen 1 and this oxygen 2, which oxygen shares? They both can't share at the same time. Like if I said, okay, we'll get rid of both and we'll make a double bond on each of them. That doesn't work. Why? Because sulfur has access to 2, 4, 6, 8, 10. Too many electrons, okay? So just one of the oxygens is going to share Some electrons. I'm going to pick the first one. And make a double bond over here. Could you have done it instead where you made the double bond off of the second oxygen? You could, okay? And what's actually happening is there's sort of a 1.5 bond occurring in both of them, or the double bond is kind of oscillating back and forth. So anytime you get to a point where you need to make a double bond, but it doesn't matter like which one you make it off of, that's known as a resonance structure. Okay, resonance structure. And they have a much neater picture here in the slides. I'll show you guys here. So we've got our SO2. And they made the double bond off the second oxygen. You could make it off the first. They're sort of existing simultaneously. Sometimes they're drawn where they will make like each one, and they'll put a set of arrows between saying, hey, that double bond is kind of oscillating or it's intermittent or between. So if you ever get to a point in your structures where you need to make a double bond, you don't want to make a double bond on everything, you just need to pick one of them and make a double bond, you've hit what's known as a resonance structure. Okay, so we are going to take this Lewis structure stuff and we're going to bring it into three-dimensional space because molecules aren't flat. When we're doing the Lewis structures, they appear flat because we're putting them on a piece of paper, but they actually move forward and back in space. So the second part of this theory is known as the valence shell electron repulsion theory, or what's known as the VSEPR theory. Valence shell electron pair repulsion. What it's saying is that the valence electrons want to get as far away from each other as they can. Okay, they are going to repulse or push each other away. The VSEPR theory is based on the idea that electron groups don't like each other because they have negative charges. So they move or create a structure that allows those electron groups to stretch out in space. What do we classify as an electron group? This is important. So an electron group is considered one lone pair of electrons. So two electrons that are by themselves on the central atom, that pair, that would be classified as one electron group. A single bond is considered one electron group. A double bond is considered one electron group. Okay, so when I'm looking at, what was it, CO2? O double bonded to C, double bonded to O, it looks something like this. Okay, this is one electron group and this is one electron group. We classify that as a single electron group. Why? Because can you break the double bond up? No, it's sealed on both sides, right? It's kind of pinched off. So it's acting as a unit. So that double bond is going to act as a single unit, can't break it up. So we want to classify each of those as a single electron group. When it's talking about lone pairs, it's only referring to lone pairs on the central atom. It doesn't matter what lone pairs you have on the outer atoms. They don't dictate the shape. So it's hard to explain this over Zoom because we're working with 3 dimensions, but you know, if you think of like my body as the central atom and my arms as the bonds, and then my hands are the outer atoms. Okay, my fingers are the electrons on the outer atoms. They don't affect the shape. Just what's happening at my arms affects the shape of the molecule. My fingers are just sort of accessories, right? So these here are really far out. They don't dictate the shape. It's just going to be what's going around that central atom. So we talked about CO2. So CO2, we would say, has 2 electron groups. All right, it's got a double bond here and a double bond here. These electrons on the outer atoms are important, but they're not important for the shape. So if I have two electron groups, how do these things get as far away from each other as they absolutely can? Because they both have negative charges. Well, they can get 180 degrees away from each other. So the structure that you get when you have two electron groups on the central atom is called linear. Linear because it makes a line, right? Does that make sense? Like if I had, a ball or a ring in the center and I had two ropes and the ropes wanted to get as far away from each other as they can, it would be 180 degrees. So we get a linear structure. What if instead of two electron groups, we have three electron groups? All right. So looking at this, I've got one electron group here, one electron group here, and one electron group here. Remember, a double bond is classified as one electron group, right? Fused together. These aren't important to the shape of the molecule. It's just what's coming off of the central atom. So if I have three electron groups, how far away can those things get from each other in three-dimensional space? Well, it's 120 degrees. So think of a pizza and you've cut it into three slices, okay, three big slices. This geometry is known as trigonal planar. Trigonal, tri because it's three, planar because it's all happening on one plane or one sheet. So it's not like this in this molecule, none of these are coming forward towards you or going back into the screen. They're all on the same plane. So anytime you have three electron groups, we're going to have a trigonal planar geometry. What if we have four electron groups? When we're doing our Lewis dot structures, four electron groups looks like this, like carbon. I'm going to do methane, carbon, hydrogen, hydrogen, hydrogen. This is what it looks like, right? Four groups. They look like they're roughly 90 degrees away from each other, but that's not actually the shape. It's not this like square planar thing. The electrons can move forward and back in space. So the shape is what's called a tetrahedral. And I am not even going to attempt to draw it, but it looks something like this. So it's kind of like a little pyramid. So in our methane, we have carbon in the center, and it's got three hydrogens pointing down and one hydrogen pointing up to make a cute little pyramid. These are 109 or 109.5 degrees away from each other. Remember, these things want to move forward and back in space to get as much distance as they can away from each other. So yes, the Lewis dot structure will give us this, but in real space, it looks like this. So four electron groups will give us a tetrahedral shape. So you want to know these. There is a graph that sort of has all this summarized, but two electron groups is linear, three electron groups is trigonal planar, four electron groups is tetrahedral. Now, in every one of these cases that we've talked about thus far, we haven't had any lone pairs on the central atom, meaning there haven't been any electrons that have been attached to the central atom that don't themselves have an atom. So the atoms on the outside have paralleled the bonds. Let's look at a situation where that isn't the case. So we've got ammonia over here. NH3, it looks something like this. We now need to start talking about the electron geometry versus the molecular geometry. Okay, the electron geometry is talking about the arrangement of the electron groups. So this is sort of what you've already done. Count up the electrons, groups around the central atom and name it. So looking at this thing here, I've got nitrogen in the center, and how many electron groups does it have? 1, 2, 3, 4. 4 electron groups. So its electron geometry is this thing called tetrahedral, right? It makes a tetrahedral shape. We can see it right here. The lone pairs push down on the other remaining hydrogens, and we have this tetrahedral shape. The molecular geometry, though, is a little bit different. The molecular geometry is saying, hey, I don't want to know what the electron groups are doing. I just want to know what the atoms look like. So if I've got a lone pair of electrons, it has an effect on this shape. What's remaining is nitrogen with 3 hydrogens, but it's not trigonal planar. You see how these are not at the same level? It's not flat like a pizza. It's sort of lifted up in the center because this negative charge is lifting the molecule up. So we have a geometry known as trigonal pyramidal, just close enough to trigonal planar to drive you crazy, right? But trigonal pyramidal is making a pyramid shape. We will do a couple of these. I want to go over them loosely first. Anytime you have these lone pairs, it always makes it a little more challenging. If you don't have lone pairs on the central atom, your electron geometry and molecular geometry are the same. How nice is that? It's the lone pairs that make the molecular and electron geometry different from each other. Let's say we had 2 lone pairs of electrons. Okay, so water. A lot of times people will look at the water molecule and they'll say, oh, that's a linear structure. It looks like it's linear on a flat piece of paper, but we need to expand it in 3-dimensional space. This is why it's always nice to do this lab in person, but we don't have it. So you can use marshmallows and toothpicks while you're working on this lab if you want to. And use the toothpicks, stick them in. They would be your bonds. Okay, so here's the Lewis dot structure. How many electron groups do we have? That determines the electron geometry. I've got 1 here, 2 here, 3, and 4. 4 electron groups. So the electron geometry is in fact tetrahedral. Think about your tetrahedral shape, your little pyramid, and rip 2 atoms off. All right, what are you left with? You're left with 2 corners of the pyramid and the oxygen in the center. This is going to be a bent structure or a V-shaped structure. This is the last structure, okay? Don't get freaked out. There's no more after this. So it's linear, trigonal planar, tetrahedral. And then if you have those silly lone pairs of electrons, you can also have a molecular geometry that can be trigonal pyramidal, or it can be this bent shape. So let's look at the diagram. Here is a diagram that shows you sort of all of this stuff. We've got the number of electron groups. Anytime your electron groups and your bonding pair is the same, meaning every electron group is attached to an atom, you're going to have... Oh. Oh my gosh, they're so sneaky. They try and divide and conquer. She's like, can I have another cookie? Did your dad say you could have another cookie? He said I couldn't have one. Well, no, you can't have another cookie. They want to put that wedge in between you, break you up. All right, so if we have the same number electron groups as we do bonding pairs, or we have 0 lone pairs, the electron geometry, molecular geometry are the same. That's like this. Same thing here. Look, we've got electron groups, bonding groups, same number, same Z, same Z. Okay. Same thing here. Tetrahedral, tetrahedral. It gets confusing when we get those silly lone pairs. They change the molecular geometry from the electron geometry. Traditionally, in an in-person class, you would have to have this diagram memorized. You guys don't have to have it memorized. You can reference it, but you have to be able to use it. Okay. So I am going to give you, well, let's go back to, gosh, I don't even know if I have them anymore. What do we have on the whiteboard? No, we don't. We had a couple things. We had NH4+. I remember that was one of them. Okay, so we had nitrogen in the center, hydrogens on the sides, stuck together, and it had a plus charge. This should be in your notes somewhere. So I want to figure out what is the electron geometry and what is the molecular geometry. Electron geometry. And I also want to figure out the molecular geometry. The electron geometry is asking you about all the electron groups around the central atom, okay? So in this case, I have, let's use a different color. I have 1, 2, 3, 4 electron groups. So what shape is 4? 4 is tetrahedral. Tetrahedral. Okay. Make a note here, 2 groups is linear. 3 groups is trigonal planar. 4 groups is tetrahedral. Okay, so the electron geometry for this thing is tetrahedral. The molecular geometry is, what are the atoms doing? Well, every one of our electron groups is attached to an atom. So the atoms are going to exactly parallel what the electron groups are doing. So the molecular geometry is also going to be tetrahedral. Anytime the number of electron groups equals the number of atoms you have around it, those two things will be the same. Let's look at one that doesn't do that. So we had in your notes PH3, right? That was P in the center, H, H, H. We stuck it together, and then we had, oh, those pesky lone pairs of electrons, okay? So my electron geometry is going to be whatever the total number of electron groups are, including lone pairs. 1, 2, 3, 4. 4 electron groups is tetrahedral. Okay, so it has a tetrahedral shape. So visualize in your mind that little pyramid, 3 prongs pointing down, 1 prong pointing up. How is this different though than this? Besides, this has nitrogen in the center and this has phosphorus. Well, this, every single bond has a buddy. In this one, 3 of the bonds have a buddy. 1 of the bonds is by itself. So think of your little pyramid shape and rip that top atom off. What are we left with? We're left with 3 prongs pointing down. So the molecular geometry is trigonal pyramidal. Trigonal pyramidal. Okay, a little pyramid that points down. How can you decide this from that chart? Well, we have 3 bonded groups, 3 bonded and 1 lone. 3 bonded and 1 lone. Let's go back over to the slides. What has 3 bonded? 3 bonded rather, and 1 lone. Tetrahedral for the electron geometry, trigonal pyramidal for the molecular geometry. So you can always reference this. Questions? You guys want to do one of these on your own, start to finish? The Lewis dot structure and the geometry. You know what? I'm not asking you. You guys are going to do it so that you know this. Okay. So I want you to do the Lewis. You can't figure out the geometry without like drawing a Lewis dot structure. So I want you to do the Lewis dot structure, and I want you to do the molecular geometry and the electron geometry. For SO4 2 minus, let's just go polyatomic ion crazy. Okay, SO4 2 minus and CO3 2 minus. Lewis structure. And you can put that up here. Then I'm going to want the electron geometry and the molecular geometry, okay, for both of those. So 719, let's come back at 7, we'll come back in 5. Okay, so sulfate, polyatomic ion. Calculate how many electrons you have. Sulfur provides 6. Oxygen provides 6, and there's 4 of them. And then there's a -2, which means we add 2 electrons. So we should have 32 electrons total to play around with. I'm gonna put sulfur in the middle. I'm gonna put those oxygens around it. Stick it together. Then we want to make the outer guys happy. So oxygen here only has access to 2. I need 8, so let's give them 6 more. Same thing with this oxygen. He's going to want 6 more to get the 8. Same thing here. And same thing here. Okay. Finish it off. Well, the 2- there. Finish it off by making sure everybody's happy. The oxygens are happy. The sulfur is happy with 8 as well. So give it a 2- charge. It's electron geometry. Well, how many electron groups do I have on the central atom? 1, 2, 3, 4, 4. So this is tetrahedral. A lot of times people will say, oh, well, there's lone pairs out here. They don't matter with the shape. Remember, those are the like outer fingers. They don't do anything to the molecular shape. It's all the bonds on the central atom. The molecular geometry is also going to be tetrahedral because there's an atom attached to every one of those groups. So same Z. CO3 with a 2- charge. All right. Carbon is in column 4, so 4 valence electrons plus oxygen, which is 6 times 3 minus 2 means we add 2. So what, 18, 20, so 24 electrons play around with. I'm gonna put carbon in the center and the oxygens on the sides. Stick it together. Make the outer guys happy. So oxygen wants an additional 6 to get the 8. Same thing with this one. This one. All right, right now I have 24 electrons on the board. So all my electrons are on the board. Is everybody happy? Not quite. The oxygens are happy. The carbon is short. I can't add 2 electrons. I have to share some electrons. Do I share it off of this oxygen or this oxygen or this oxygen? Doesn't matter. I just need to pick one of them. So that also makes this a resonance structure. Okay. I'm going to pick, I don't know, this oxygen here. So I'll erase a pair and move it over. All right. Now everybody's happy. The electron geometry. Well, how many electron groups do I have around the central atom? 1, 2, 3. 3 electron groups, trigonal, planar. Think about your pizza cut into 3 slices. I don't have any lone pairs on the central atom, so my molecular geometry is also going to be trigonal planar. Even if it's a resonance structure, even if there's a double bond, we still say that it's, as long as there's no lone pairs, it's the same. Any questions on that? On those? No? Okay. So in your labs, if you can, when you get to a Lewis dot structure that is a resonance structure, just make a little note, say like RS or resonance structure, just so that you get in the habit of identifying if it happens to be a resonance structure, okay? Let's head back over to the slides. Okay, this thing talks about everything we just talked about, so blah. All right, the last bit of this is talking about electronegativity and polarity, which relates to why oil and water don't mix. There's a reason, and it actually has to do with all this molecule stuff that we've been talking about. The water has this tendency to want to push out or expel the oil. Why is that the case? Well, looking at the water molecule here, the water molecule is what we call a polar molecule. Sometimes you may hear them saying water is the universal solvent, right? Oh, just put some water on it, it'll dissolve it. Well, it won't dissolve everything. But it dissolves a lot of polar things, okay? Polar things dissolve polar things. Polar things do not dissolve nonpolar things. So water doesn't dissolve oil. That's why we have to use a secondary substance like soap. In this bond here, the oxygen and the hydrogen are sharing 2 electrons, but they're not sharing them equally. The oxygen is actually much greedier for the electrons than hydrogen is. This is known as a dipole moment. And I guess they want to talk about electronegativity here first, but so an atom's ability to attract electrons is known as its electronegativity. Oxygen has a higher electronegativity than hydrogen does, meaning on average, the electrons are shared more with the oxygen than they do with the hydrogen. So you get what's known as a dipole moment. And we can see in here, there's an oxygen and a hydrogen. And then this is an electron probability cloud. And we can see the electron is much more likely to be around the oxygen than it is the hydrogen because this has a stronger pull, okay? So because the electron hangs out more around the oxygen, this side gets sort of a negative charge and this side gets a positive charge. We say this is a polar bond or a polar covalent bond. So anytime you have a covalent bond or a bond where they're sharing electrons and they're not sharing them equally, one of them is greedier for the electrons than the other one, we say it's a polar covalent bond. If we look at the values for electronegativity, and these numbers are sort of arbitrary, Pauling, who was a famous chemist, he sort of set fluorine, which has the highest electronegativity at 4, and then everything decreases from there. So 4 has the highest electronegativity. There's no unit though on this. Oxygen is just 3.5 of the 4. So you take 3.5 divided by the 4, and that would be how strong the oxygen's pull is against the fluorine. So it's less than the fluorine. And they decrease as you move down and to the left, which follows our trends, right? Things up here, like electrons, things down here are pretty much giving electrons away. So if you have a fluorine and a fluorine, like F2, the diatomic F2, those have the same electronegativity, right? The fluorine has a 4 and the other fluorine has a 4. So they're sharing the electrons equally. We would say that equal sharing is known as a non-polar covalent bond. Non-polar because there's no polarity. There's no difference. So there's no when we're looking and they use the example of chlorine here. The electrons are being shared equally. So we have these equal bubbles. There's no positive side here and negative side here. They're nice and balanced. So this would be a non-polar covalent bond. If you have a really large difference in electronegativity, like you are a metal and a non-metal, so you have fluorine combined with sodium. Okay, this is a huge difference in electronegativity. If I take the 4 and I subtract the 0.9, it's 3.1. Anytime you have a large electronegativity difference like that, this atom is like, whatever, dude, I don't even care. Just take the electron. So he gives the electron to chlorine. Chlorine is super greedy for the electron. It forms a charge differential and they stick together, or you get an ionic bond. There's a cutoff with the electronegativities, and it goes like this. If your difference in electronegativity is 2 or greater, we say it's an ionic bond. The difference there is so great that the electron just transfers. If the difference in electronegativity is 0.4 or less, this is pretty much when you're dealing with like the same element. So chlorine bonded to chlorine, we say that that's a pure bond or a non-polar covalent bond. They're sharing the electrons equally. And then there's this intermittent step in between where the difference is like 0.4 to 2, where the electrons are being shared, but they're not being shared equally, right? The electron is kind of hanging closer to the thing with the larger electronegativity. So you can have a non-polar covalent bond, a polar covalent bond, or we just jump into an ionic bond. So how does this relate to molecules? Well, just because you have a molecule that has polar bonds does not mean the molecule itself is polar. So don't confuse polar bond with polar molecule. A polar bond is when 2 adjacent atoms don't share electrons equally. A polar molecule is when you have polar bonds that add up and don't cancel each other out, or there is some sort of a imbalance in the molecule. So let me show you an example of a balanced situation. The bond between carbon and oxygen and CO2. is a polar bond. Polar bond. Okay. They don't share the electrons equally. The electrons hang out by the oxygen more. But the molecule as a whole is nonpolar. Why? Well, because we've got a tug of war where the electrons on this side are pulling to the left and the electrons on this side are pulling to the right, and the pull is equal and opposite. So the molecule remains balanced. Anytime you have something that's balanced, it's nonpolar. Balanced molecule is going to be something that's nonpolar. Okay. Let's look at a situation where it's not balanced. What if we look at water? And I don't like that they didn't put the lone pairs of electrons. It's like the whole point of it. But water traditionally has two lone pairs of electrons here, right? Those two lone pairs of electrons have an effect. It pushes these vector arrows down. So water isn't linear. It's a bent structure, right? And because of that, the molecule is asymmetrical. It's like they're playing tug of war, and they were going to originally have 4 ropes, right? Because they have 4 electron groups, but only 2 people came to the tug of war. These 2 people drank too many beers and aren't coming. So now everything is going to get sort of pulled in this direction, or there's an asymmetry to the molecule. Another way we can say this is the lone polar pair. Okay. The lone polar pair. If you have lone pairs on the central atom, it's polar. That will really cover 98% of molecules. So, if you identify a lone pair, you'd say the molecule is polar. We go back to our here. These 2 structures here. If I was to say, hey, is this thing polar or nonpolar? Well, just look at what's happening on the central atom. Sulfur's here. There are no lone pairs. So I would say this thing is nonpolar. Nice and balanced. Also, this thing, no lone pairs on the central atom, even though it has a double bond here. Know that double bond sort of oscillates around because it's a resonance structure. So this would also be nonpolar. What about pull back up that NH3? Okay, we've got nitrogen with 3 hydrogens. We have a total of 8 electrons to mess around with, stick it together, and there's 2 lone pairs here. Is this molecule polar or nonpolar? It is polar. Lone polar pair. Anytime you have polar, or anytime you have lone pairs on the central atom, it's polar. Again, think of it like we've got that tug of war and there's 4 ropes. Well, 1 person didn't come to pull on the ropes. So there's a imbalance. Any questions on a molecule being polar or nonpolar? Things that are polar, like this molecule here, will dissolve in water. Likes dissolve likes. So polar things dissolve polar things. These 2 molecules over here won't dissolve in water. They would want to dissolve in something like hexane or something that's a nonpolar molecule. So how does this relate back to water and oil not mixing? Well, water is a polar molecule. Water is a polar molecule. Oil is generally a nonpolar molecule. So water has this side to it that has a positive charge and a side to it that has a negative charge. Like if I draw the molecule out, O, H, H, stick it together. There's some lone pairs over here. This side of the molecule tends to be negative. These 2 sides of the molecule tend to be positive. So it's like a magnet. Well, what's going to happen is this positive side is going to attract the negative side of an adjacent water molecule. Right? Here's a negative side and here's a positive side. So this is going to attract and this side sort of attracts. So what happens is all the water molecules like clump together, or they attract together like magnets do. Think if you had a beaker full of sand and you put a bunch of flecks of metal in it, what would the metal flecks do? At some point, they would like gradually gravitate towards each other and clump up in the middle and push the sand out. The water is doing the same thing with the oil. All the water molecules are sticking together and they're saying, hey, you know, oil molecule, you're too balanced. You don't have a polar quality to you. I'm going to push you out. So you can see it happening here where we've got all the water molecules clumping together, and they usually tend to be more dense than the oil. So they'll be on the bottom of the beaker. And then the oil molecules kind of get left to themselves. So how does soap work? Soap is a really, really cool molecule. It's usually made by taking some sort of fat or oil, which is a nonpolar molecule, and it undergoes this process called saponification, which is where you take lye and you pretty much take this really long oil molecule and you cut off the end and you put a polar head on it. So hypothetical soap molecule would look like this. There's a really long nonpolar towel, and then boop, right at the end through the process of saponification, we gave it a polar head. Now, this soap molecule is acting like a bridge. What is the nonpolar side going to stick to? It's going to attract the oil and the grease. Right? All that greasy, oily stuff is going to stick here. What is the polar head going to attract? It's going to attract the water. So, you know, if you've ever washed your hands, like you have greasy oil on your hands and you just run your hands under water, it doesn't do anything, right? You have to use soap to create a bridge. So the soap will grab onto the oil on one end, it'll grab onto the water that's rushing over your hands, and it'll remove the oil from your hands. So cool. Soap is awesome. Very, very cool substance. So yeah, you probably want to be comfortable with like how soap works, basics of it, really just knowing that there's a polar head and a non-polar towel, and it acts as a bridge to connect these two things that would normally repel each other, right? And I believe that is it.